Hi, everybody. Today's lesson continues with the exponential unit, the next one we're studying here. So we're going to look at exponential growth. We're going to look at an example of it, an activity, data collection and analysis. And I also want to start out with a summary of the exponential information that we saw yesterday for the first time. Right, so let's get going on that. So the summary, I'm going to look at what the exponential data looks like, what the exponential equation looks like, remind you of how we determined that yesterday in the previous lesson. And then we're going to look at the exponential graph looks like and look at an example. All right, so the way the numbers look is simply that we'd have the numbers, ungroup that thing. We'd have the numbers would be like this, where you'd have this growth factor multiple that the numbers are growing by. And we'll talk about what the growth factor can be as well when we look at the equation in that. But the key is if the multiple going from one to the next is always the same. And so you can look at it as like the second number divided by the first number always. So maybe I'll put this in as number one and number two kind of thing. So the growth factor multiple is number 2 divided by number 1, right? So that's the multiple there. Yeah. So if that's always the same, then you've got a situation that is exponential. And then yesterday we looked at the numbers, how this would work. And so basically for the first one here, you're multiplying by the growth factor once. The second one, you're multiplying twice and so on, right? We actually started with like 0 and a number to start with. And so how it worked in there was you multiply once to get the first one and multiply twice to get the second one and so on and so on, okay? So basically we found that we had an exponential equation that made sense, which we did like this, okay? So in the equation, we said, okay, well, we got a starting value. So have like an initial value I. I might show this as well as we go through here, show both because I can point it out here. So we have an initial value on the graph I that we're starting with, or the initial value here in the table would be your starting value as well, okay? And then, of course, we're multiplying by that growth factor each time. And we multiply a certain number of times, okay, to get to the whatever step we're looking at. And so this growth factor here can either be as a percent, it could be a 1 plus R, or the R is the percent as a decimal. So this is the percent as a decimal. Or it can just be a growth factor multiple, like a 2 for doubling or 3 for tripling and so on, right? The other thing to watch for is that if the, say that something was doubling every 3 years, like in the example yesterday, you'd have to have this divide out by this every year or every 3 minutes or whatever. I think the dough was every 3 minutes, right? So if instead of being 1, 2, it was 3 and then 6, right? You can tell we're going by sets of 3, then this would be a divide by a 3. Okay, from this idea here. So we're going up by 3s, and so that would correspond to that right there. Okay, same deal up here. There's that equation we just wrote. I'm just showing that that's the equation of that line. And if you're visualizing some things on here, you got the initial value, you've got your multiple, your growth factor that's multiplying. And again, same deal as I said a second ago here. You've got your percent as a decimal, 1 plus the percent as a decimal, or it could be a number like 2 for doubling or 3 for tripling. Okay, so the other part I put on the graph here was that we have the standard XY graph, or it could be, time in minutes right here versus, population of time in years, maybe number of years and population of wolves, or whatever the case may be, right? You have variables that match sort of the situation. The other thing we talked about was if this is a double right here, kind of an interesting one to watch for, right? If you're looking for the time it takes to double, if that was a 3, that matches the orange that I showed already on the other stuff. You'd have an over 3 in the exponent up here, just like that, if it's there. If it's a 1, then this would just be, this number would just be a 1, right? So it's either a 1 or 3 or a 1. Or, whatever the number is. If it's something's doubling every 17 minutes, then you have a divide by 17. And so an exponential example, we have an initial volume of 100 liters tripling every 5 years. Okay, so initial volume of 100, it's tripling, so it's a 3, and it's every 5 years, so it's a divide by 5. If we switched it to be every 1 year, then that would just be a 1. In other words, that would just look like n overall, right? So this would just be n, but it's understood to be n over 1. Okay, so there's a summary of all of the stuff from yesterday. Okay, so we want to sort of put that to use today. Today, it's a activity that you can carry out easily. You just have to get a bunch of coins and carry it out, but we'll just look at the idea of it here as well. So you're starting with 1 coin in a cup, and you're basically flipping the coin onto a desk or table or floor or whatever. If a head is showing, you just put it back in the cup and do it again. If it's not a head showing, then you want to pair it up with a head, right? Another coin, in other words, and put them into the cup. So then you'd have 2. Okay. So if we did that and we got lucky on the first try and we didn't have a head, and so you're pairing up, you get 2. I'm just going to show like possible numbers here, and you could do the activity and see how close you get to my pattern, right? So when you flip 2 coins, there's a 50-50 chance that each would have a head or a head showing or not, right? So basically, it seems like it'd be possible that this number could be either 2, 3, or 4, right? So 2 or 3 or 4, I might go with 3. Then when you flip 3 coins, right? You could have 3 heads, you could have 3 tails, you could have whatever. So basically, if you have 3 tails, you're going to pair up coins with each. So the biggest number we could get is 6. The smallest number we get is a 3. So let's go with like a 5. With a 5, biggest number you could get if you paired up with every single one was tails, you'd get a 10, or the lowest you get. In the middle of that would be like 2.5, so you'd have like a 7.5. So let's go with 8. Again, pairing up, if they were all tails, you could get 16 total because you'd add 8 to pair them up, or you'd get maybe none, which would be just 8. So half of that, let's do. So we'd add on 4, so we'd get 12. And so basically, you're probably noticing that there's a good chance you're going to add on about half because there's 50-50 chance of your coin flip and so on. So if I just went with those numbers, you see what you get when you do your experiment. But the idea should be pretty clear here that if I add 6 onto that, I get 18. And then half of that would be the 9. And so the 9 plus the 12 would give like a 21. And then 21, half of that isn't an even number, but it's about so 21 divided by 2 would be like 10.5. So if we added on 10 or 11, we'd have 31 or 32. Let's go 32 just because it's divisible by 2 really. And so we get add on 16 to that. So we're going to have like 48 or so. So we could go like 48 or 47 or something like that just to kind of, give it some randomness. 47 divided by 2 is 23 plus the 47. So you'd have like 70 or 71 or something like that. Right? So you might need, depending on how many trials you do, you could quite possibly need 70 or so coins. So raid the piggy bank or just go with these numbers. You don't want to have fun with it yourself. Obviously, you could just go ahead and graph this thing. I'll let you graph it by hand for your submission, but we're also going to be doing with technology. And you're going to show a picture, just submit a picture of your screen with your lesson, with your assignment. 30, 35, 40, 45, and then the top one is the 50. So you would start out with your 0, we're at around 1. Then at 1, we're around 2. It's a little dicey to try and get these graphed accurately, but approximately as best we can. Finally, we get to numbers that are a little easier to do, like the 5 and 8 and so so on. So just keep going. Just graph those. So the part that's new here, this is just flipping coins and counting and looking at numbers. If we think about our summary, if we were to think about what the growth factor is, this would have been 2 divided by 1. So this is times a 2 divided by a 1, which means times 2 in other words, right? Let me just do times 2 there. But point out that that was from 2 divided by 1, if you needed to think about it. Here we're going to have a 3 divided by a 2, which is a 1.5. And here we're going to have a 5 divided by a 3, which is a 1.67 or so. 8 divided by 5 gives us a 1.6. 12 divided by 8, I think it's going to be 1.5. Yeah, 1.5. The 18 divided by 12 is also 1.5, because I did some exact numbers, right? 21 divided by 18. That's really low. 1.16. 32 divided by, I must have sort of messed up on that number a little bit, but then we went back to time, and that's just by random chance. That could totally happen. And 47 divided by 32. So the reason I'm doing that, of course, is in our summary we saw that. Go to the art room for a quick meeting. And finally at 1.51. Okay, so you can see that the growth factor should be expected to be around 1.5. Now, approximate if there's random chance going on, of course, right? But that's what we should be expecting based on our understanding of the odds of things happening, and we should notice from this too that means, because they're all about the same. So let's add that in, right? They're all about, they're all around this, around 1.5. So that means we're talking about an exponential situation based on what we talked about in our summary. So you just graph it and so on. Okay, so the new part is to do a linear and exponential regression to see how they fit. And then you can use the models to predict how many coins there'd be if you did this 100 trials. So to do that, I'll show you 2 ways. Exponential, or using just a spreadsheet. It's a pretty standard way to show it. I'll show you a couple things to do with spreadsheets. So you would just load up either Excel or a Google version of it, or whatever you have access to. Okay, so all Upper Canada students have access to Office 360. Other school boards sometimes use Google, so whatever the Google spreadsheet's called. It's a nice way to do this if you wanted to have this be able to fill in numbers for you more easily. Just get rid of my writing here. Typed on the smart board. Typed on the smart board and it wrote in there with a dot. So get rid of that thing and put my 0 back in there. Okay, so all I wanted to show here is, instead of having to type 1, 2, 3, 4, I could say equals the previous cell plus symbol a 1. And it'll automatically spit out the 1. And then I can grab that corner and drag it down, and it'll just keep filling that pattern, that formula in over and over again. I could also say copy and paste, and it continues on, right? Control C and Control V, like normal, or even in the home button here, if we did edit or copy in this one. Anyways, Control C and Control V is the easiest way, or right click even, right? I can do copy, and I could do right click, paste. I'm just showing, how you can use the formula feature to save yourself some time. There's numbers plugged in. These are different than the ones I did in the lesson, just by random, trying to approximate random chances here of coin flips. I'm just going to show how to do this. Okay, so if you're doing a regression, load up Excel, type in the numbers, and then you're going to highlight the box of the numbers, where the numbers are, and you're going to go to Insert. So Insert, And then you're going to go to the scatter plot, and you're going to choose this one, which is just the dots. Okay, so it looks like this. You just go highlight the box, insert, go to this one, go to this one. Okay, so you have the graph. That's what your one by hand would look like as well, of course, right? So you have the graph, and then you can add a trend line. So I'll go to the page where it says this, right? So insert that, and then right-click on the data, choose Add Trend Line, and then you can choose various relationship types. Okay, so choose your relationship type. You want to choose to display the equation and also display the r squared, and I'll explain what that means in a second here. When we get to it, I'll just tell you, tries to tell you how good of a match it is. It's not actually super useful for what I've seen. Anyway, so add trend line. If we tried to go with linear, which the spreadsheet's automatically trying to do, you can tell visually it's not a great fit. If we went down and said display the equation and the r squared value, you can see it's r squared value. If that number r squared is close to 1, then it's a good match. And it has to be really close to be considered a good match. Like 0.79 is, 79%, let's say, or whatever, right? It's kind of close to 1, but it's not close enough, obviously, to represent a good match. Okay? So that's, just the linear trend line. So on your assignment for your numbers, or whichever ones you want to use, I guess, you'd have the linear regression, and you'd have what the equation is. So you'd have like y equals, right, the equation that was there. And then if you put in the value of 100, right, so basically y equals mx plus b, whatever these numbers are, right, all you're going to do is set this equal to 100 and see what the model would predict. And then the exponential regression we'll do next, which is just a case of choosing a different, choosing the other over here, choosing the other one, right? So basically right-click trend line, instead of linear, we're going to make it exponential. So this one, it doesn't do this to me, but there we go. I had to delete them. Usually you just choose one or the other, and it just shows the one or the other. But so format the trend line here. We're going to display the equation and the r squared value. So it's giving us this result here of 1.2855, and then e to the power of, and that's a bit of a pain. I'll show you what that means, okay, what that's about. So this 1.8 value is kind of an equation, kind of an exponential equation, but it's a little different. Okay, so it's giving it in terms of a natural number e. The base is as e. It's a special number, just like 3.14 or pi for circles. E, if you're curious, is a special number because it makes the slope of an exponential function always equal to the value of the function itself, value of the line you're drawing. So slope from grade 9, you can tell that's around 25, right? So this slope would equal 25. Don't need to know that for this course, but I just thought I'd tell you. So if we wanted to convert it to proper numbers for what we're talking about, the actual growth factor going from one number to the next, right? What is the multiple to get from this value to this value, and then this height to that height, and so on, that times by what? All you have to do is do that power, right? So that 0.4033 power that's given from the regression, you do the 2.718, the special number like pi, it gives you the value that we're saying. It's like around 1.5. Right? So check, it makes sense. Okay, so that's just an exponential regression, clearly a much better fit. And so we could make the equation, of course, then just be the y equals, the initial value was 1, the 1.5 is our multiple, and an x. Okay, so that equation, yours will probably be similar to that, hopefully. I could have used, by the way, the 1.496, but it's so close to 1.5. I just put it on there. So for this one, we would have here, not letting me paste right now. I'll just write it in. So y equals the 1 times the 1.5 to the x. Obviously, same deal. If we put in a 100, see what we get. It would predict how many coins you have after 100. Looking at this, of course, which equation fits best and why? Obviously, we know you could communicate and say, well, we know it's exponential because we have about the same growth factor the whole time. And yeah, so this actually, I kind of went ahead with this at the beginning, but it was sort of a, compare your results and then go back and so on was the way I kind of intended it to be originally. But yeah. All right. So that little move there. So that's the regression with the spreadsheet with Excel. And kind of a nicer way to do this, it might be easier for you because Desmos is easily just a website people can easily go to. If you go to Desmos, which is right here, so the steps for it, I'll go back to my page here. You're going to go to the plus sign, you're going to go to table, and you're going to enter in numbers. Okay, so plus sign table, enter in numbers. Let's do that. Desmos, plus sign, table, enter in numbers. So we're going to enter the starting value, and then after 1, 2, 3, 4, 5, 6 trials, let's just do, how many did I have before? And enter those numbers in. So I had numbers of, it would let me copy and paste. Let's see. Copy. Pretty good. So we'll see. Nah, it's not letting me. All right, so we had 1, and then we said 2. We need to. Easier. Like that. And I want to see the spreadsheet as the other. See the screen at the same time here. Desmos. Okay, so 1, 2, 3, 5, 7, 11, 14, 21, 31, 47, 69. All right. So numbers are in, and it's automatically graphing as we go. You can see the graph there. You can change the scale if you want, changing what your max and min values are and so on, but it looks good enough, really. Especially if I zoom out a little bit, I can see more of it. And so in order to do regression with Desmos, you just go to a new equation, and you have to use the variables you started with. So see how it's y1 next one. So I'm going to do y1, and then instead of equals, we're going to actually use on the top left of the keyboard this squiggle. It's called tilde, but use the squiggle, and then the format for the equation, you can use any letter you want, but it has to be a number, and then a number to the power of the x1 variable. Okay, so power of x1. I just used the little hat, little triangle, upper or whatever. Probably use the keyboard for it or whatever too. But anyways, so as soon as you type that in, it goes ahead and does a regression, and it gives you that 1.47, about 1.5 number that we got from the spreadsheet regression. It's approximating the initial value is about 1.39. We of course know the initial value was actually 1, but the pattern that fits this best is that. I wonder, you might be able to like make this be. No, it doesn't let you. Some programs would let you assign a particular initial value that you know is true, and then make the best data that fits that goes through that. But Desmos doesn't have that feature apparently. But yeah, so that just gives you the number directly, so you can get an exponential regression using Desmos as well. Arguably, maybe a little bit easier because it doesn't use E on you, but then it does have this little weird bit about having to use Y1 and X1 and the squiggle and so on. Once you know how to do it, it works pretty good. So that is it. Yeah. So I'm hoping to see, your data from your coins, your graph, your equations from your regressions, screenshots of what you've done. Just, take a bunch of pictures of it, post it as your, don't worry about putting it together into a file or whatever. Just take pictures of this and pictures of this and, pictures of each thing as part of your results, and of course a picture of your page that hopefully you can print out and send in as your assignment, right? So idea of this lesson, of course, just give you a little more experience with our new unit and the equation and all that. Hopefully that works for you. All right, I will close off here. See you next time.